So my name's Joe Stagner, and today it's a little bit out of the main theme of the conference of strict controls and commissioning, but I'd like to share with you clean electrification of building and building systems, because it has a lot to do with controls and the kind of systems you're going to see, and some differences from what you might be used to doing with commissioning buildings and energy systems for those of you involved in that. All of the usual slides at the beginning. What we hope to do in this is tell you about how to electrify building and heating and cooling. And it may not be what you think with the old-fashioned electric heaters and so forth. That doesn't work real well these days in terms of cost and so forth. But I'll show you the way Stanford did it for about 15 million square foot of research and university space. And I'll explain why we did it and what the big benefits are. And I'll also explain why thermal energy storage does a lot of the same things that battery storage do. And you'll hear a lot about electrical microgrids these days, and there's a lot of development of electrical microgrids, including controls and storage and things. But when it comes to buildings and building energy, thermal storage is the optimum thing to do before electrical storage. So I'll tell you why that is and where we sit with adding electricity storage to the Stanford campus. And that leads into the last item, which is energy microgrids. Again, everybody and their brother from Elon Musk is, who I like a lot, by the way, is pushing electrical microgrids. You know, solar on your roof and a battery in your garage and an electric vehicle and these kind of things. When it comes to buildings and building energy, really a total energy microgrid, not an electrical microgrid, is the way to think of it. You got to bring the thermal into it, the heating and cooling, because that's 2/3 of the equation. And hopefully this will explain why that's a value. But just for fun, I thought I'd start with an energy Rorschach test. So I'll show you a few images and you can think about what they might mean to you. And as we go through the presentation, you'll see what these ink blots really mean. Here's another one, nice and colorful, a lot of different shapes there. There's another one. Hopefully at the end of this, those things will have more meaning to you than they do now. So a lot of you probably know this, but buildings consume about 40% of the energy in the Western world, the developed world, and account for a like amount of greenhouse gas and other emissions. So having well-run buildings that are designed well, and as I will mention, move to electricity, are a key to this. And I can say with confidence that clean electrification is going to be the predominant path to what you see in buildings in the future. It's what you're going to see with vehicles, with electric vehicles replacing internal combustion engines and so forth, because in the end it's a lot cheaper to build, operate, and maintain. With cars, the prices will be coming down, and probably 20, 30 years from now, there'll be half electric cars or more on the road, I expect. For buildings, it's not widely as known and understood as people are seeing with cars, why electrification is important and what it can do. You can contrast that with a car pretty easy. You got an internal combustion engine and oil and gas and all those systems that go with it. And an electric car is pretty simple. It's a battery and an electric motor and not much to do there. They run real well. Well, buildings can be the same, and I'll help you see why, hopefully. This is the first thing that I like to show about how to electrify buildings and why it's efficient. And it's not in using the old-fashioned electric resistive heating that was popular in the 60s when there was the big electric home movement, and they were building lots of electric home communities around the country. Electric resistive heating is very inefficient and therefore very expensive. So to show you just how inefficient it is and compare the other way to heat with electricity that's far more efficient, I'm presenting this slide, which puts everything on a natural gas basis. Because it's hard to compare the efficiency of systems if you don't do it on a common fuel basis, right? So let's suppose all of our electricity and all of our energy was made with natural gas. That was the only fuel, and you want to know what's the most efficient system. Well, if you look at electric resistive heating up top, you'll see that to get 3,413 BTUs of heat, which is 1 kilowatt hour, you'd have to put 6,826 BTUs of natural gas into a grid or on-site gas power plant that's about 50% efficient. That's about the state of the art these days. They have them more than 50% efficient, but the average fleet in California is about 45 right now. So 50% efficient. So like with electric resistive heating, a lot of homes are heated with gas, and a lot of folks have moved to gas for their hot water and space heating for a good reason, because to get that same 3,413 BTUs of heat from, say, an 85% efficient home hot water heater or furnace, then of course you only need to put in a little over 4,000 BTUs. So given a choice, it's better for society to use 4,000 BTUs of gas directly in on-site heat production than putting it in a power plant and use electric resistive heating at your homes. But what a lot of people forgot about, which have been around a long time, are electric heat pumps. So unlike the first two methods, which take raw energy, gas or electricity, and convert it to low-grade heat, an electric heat pump, you just add enough energy to allow the pump to take low-grade heat that already exists and turn it into a form you can use it. So it's not creating heat out of energy, it's using energy to do work, to harness heat that already exists, repackage it in the form you need it, and redeploy it. So in this case, I have a picture of Stanford's big heat pumps, and we want 160-degree water out of our heat pumps to heat our campus, because that's how our building HVAC and control systems and our various heat exchangers are sized. With a new house or a new campus like we're building in, we call it our Redwood City campus, about 10 miles north of the main campus, since we're designing those buildings and all those heat exchangers and controls now, we're using 120-degree hot water. You know, you don't need 300-degree steam to get 78-degree air out of a register to heat a room, right? And you don't need it to make 120-degree water or 110-degree water for your bathing and your clothes and so forth. So we've been overusing cheap energy thus far, not being very efficient with it in steam systems and so forth. But now with the challenges we face in energy and the environment, we can go back to some of these methods that have already been proved to be a lot more efficient. So in our case at Stanford, with 160-degree water we went out at our main campus and 120 at our new campus, you can see how much fewer BTUs of gas it takes to put into a power plant, on-site or off-site, to make the electricity to drive the heat pump. It's 1/4 to 1/6 the amount of energy as the other two methods. So that's why we spent $500 million and have changed the entire Stanford campus to be electric and to use these heat pumps, and why our new campus, 1.5 million square feet, is equipped with the same system. Now this only shows if you were to use the heat pump to make heat only. If you were to, say, suck the heat out of a geothermal well, ground source heat exchange well next to your building, or a body of water or out of the air. But the fact is, buildings have to be cooled. And a lot of modern buildings like these and other big buildings do a lot of simultaneous heating and cooling. You might have to temper air down to knock humidity out of it, and it gets too cold, so you have to warm it back up to go into the main building and so forth. So that's a big opportunity, that if you're going to be removing heat from the building cooling and you need heat for hot water, well, the heat pump can take care of both. And so if you want to know what the opportunity for heat recovery through a heat pump at your building is, or your house or anywhere, simple method is shown here. If you just know every hour how many BTUs of heat you need and how many BTUs of cooling you need, you simply compare the two for every hour. This example shows, say, for a winter month and a summer month. In the winter month, obviously, you need more heat than you have cooling. In houses, you might not have any cooling, but in buildings like this, you'll even have cooling in the dead of winter. And so it's just the lower of the two numbers. If I have 10 BTUs of cooling demand and I have 20 BTUs of waste heat from the cooling process in summer, well, I can meet that 10 BTUs of heating demand in summer for my hot water and things, even though it's scorching hot outside. I still have some leftover heat to throw away through my evaporative cooling towers or my air cooling towers or whatever. But just like at your house, if you have a house in Vegas and it's 100 degrees outside and your air conditioning and someone turns on the hot water tap in your house, natural gas is probably kicking on in your garage through your hot water heater to make hot water come out your faucet. And you say, I don't get it, it's so hot outside, and I have 140-degree refrigerant going out to a condenser on the side of my house. The air is being exhausted, it might be 110 degrees, so that refrigerant's got to be 130, 140. Why not just take that refrigerant loop and put it in your water heater tank and have it keep the water hot for you and use that? So that's basically what a heat pump's doing. And they make them for your house. They make them all the way up to large commercial size. And if you ever want to see the whole overlap, it's a very simple mathematical thing. It's the smaller of the two numbers of your cooling or heating in a given hour. But also show why, if you use thermal storage, it'll work even if there's no overlap. So in the desert here, you don't get cold at night and hot in the day. Well, if you're air conditioning in the day and you're throwing all that heat away, what if you could just save it in your hot water tank and use it at night when the place gets cool rather than throw it away? So the heat pump plus thermal storage allow you to not only take advantage of all this, but also to shift when you're using that thermal energy so you can save it when it's not needed, shift it to off-peak electricity hours, and so forth. When you look at it kind of on a daily scale, here's 3 examples from Stanford, summer, winter, and the shoulder seasons. You can obviously see the higher cooling peak in summer, but there's still a consistent amount of heat needed in summer for hot water for dorms and buildings and tempering cold air back up to the temperatures we want it in buildings. And so that thermal overlap shown in green is the opportunity for reusing heat with a heat pump rather than making it new by burning gas. And you can see for the other 2 seasons that throughout the year there's always some amount of heat overlap for that reason, or heat overlap need. If you look at it for a whole year, it looks like this. So these are the months of the year on the x-axis and the energy on the y-axis, with the heating being below the x-axis and the cooling in blue above the x-axis. So you can see obviously more cooling in summer and the bright blue is needed, and more heating in winter months. And the overlap is shaded of the two, and it shows that at Stanford, about 80% of the heat we use each year can be made just by harvesting with heat pumps our own waste heat from cooling, turning it into hot water and using it. And so when we found that out in 2009, when we were starting to look at new energy systems for the campus to replace our cogen plant, which was the contract was going to be expiring in 2015, and we found this out, it became a real aha moment. And so the engineering then started to say, how can we take advantage of this? This just compares in quick schematic the basic 3 energy systems for buildings. You could have a cogen plant like you have on the left for a collection of buildings. Most downtowns, universities, military bases, and airports all have these cogen plants, or they have district energy systems that cogen plants feature. And you got a big old pipe of natural gas going to your combined cycle turbine or your internal combustion engines, produce heat and power. Some of the power goes directly to buildings for lighting and so forth. Some of the heat goes to buildings for hot water and space heating. And then some of the heat goes to steam chillers, and that's the way a cogen works, but it's a 100% natural gas option, so it's not a very sustainable thing. So those that want to eventually move off fossil fuels for economic and sustainability reasons are looking for opportunities and electrifications. That the conventional separate heat and power just to the right shows your standard boilers and chillers arrangement. So you've got gas hot water boilers making the heat for your buildings, or a hot water heater at your house. You've got an electric air conditioner at your house, or electric chillers and evaporative cooling towers for your building. That's the conventional thing, and you're getting your power from the grid. The scheme on the right, which we've moved to, we call it combined heating and cooling. Just like a cogen gives you 2 things, power and heat for one energy source, a heat pump, or heat recovery chiller as we call them, gives you 2 things for one source of energy too, the source of energy being electricity, and you get heating and cooling both from them. So this shows how the heat recovery scheme works and how it's the key to unlocking electrification all the way from your house all the way up to big giant buildings. It works. So the basic overall components of a system for any building or collection of buildings for clean electrification are a heat pump or heat recovery chiller, and chillers and boilers or hot water generators to handle the margins that you can't meet with heat recovery. You can also use ground source heat exchange and other things. You don't have to use these. If you want to make the system even more efficient and cost effective, add hot and cold thermal energy storage. And I'll explain to you what we call model predictive control software that runs the whole schmeal and does it far more efficient than humans. It's like an autopilot flies an airplane, a little bit better than a pilot can. Well, we've developed software that'll fly the whole scheme, and it's an autopilot you can turn on and off, and we have some proofs of why it's so much more efficient. So then here's what the system looks like for our campus. It's been operational since 2015. We have the heat overlap shown in gold there is handled by the 3 big heat pumps off to the left. And for the cooling in summer, where we don't have a home for the heat, you can see for about 8 or 10 months of the year, there's no red at the bottom of that gold. In summer, 100% of our heating needs in summer have been met through our air conditioning. It makes a lot of sense, and it works all over the country, from Boston to Phoenix. It's just you get a lot more of it for a lot longer in the desert and hot areas than you would up in Boston. Maybe only 4 or 5 months of the year in Boston, there's a net surplus of environmental heat being applied to buildings. But for 4 or 5 months, even in Boston, 100% of the heat that they need for heating and hot water can be met first using their own waste heat that's been going up cooling towers in the past, but now it can just be turned into heat and used instead of throwing it away. They won't burn so much natural gas. In winter, we only have a little bit of heat that can't be met with heat recovery because we have a mild climate, and we can burn natural gas and high-efficiency hot water heaters and so forth to do that. Or I could use my heat pumps and suck it out of the ground if I want to put it in a ground source heat exchange well. Or if I had a body of water near me, I could just suck the heat out of that. So it doesn't have to be natural gas heating for that red part, but you can do that. And you see our big hot and cold water tanks there. This is the model predictive control software. So when we came up with the scheme and we could tell that we want to deploy these 5 basic components for energy system for a campus, which is heat pumps that do both heating and cooling, chillers that do just cooling, hot water generators that just do heating, and then hot and cold thermal storage. You have these 5 major components. Trying to figure out how to use all those in the best way was the engineering challenge. And so we developed some software that looks 7 days in advance to always capture a weekend at all 168 hours coming up. And it says, for those next 168 hours, how much heating, cooling, and electricity do I think my collection of buildings needs? And it can do that by looking at how much heating, cooling, and power those buildings needed for a similar day anytime that year or the last 5 years or whatever. So you get some standard demand profiles that you get. If you've tracked that information like we have for years, you have a big family of data that says if it's going to be a high of this and a low of this, and the humidity's like this, and school's in session, and it's on a weekday, not a weekend, then here's likely going to be the heating, cooling, and power demand pattern. So you can predict that fairly reasonably if you have some data. Armed with that information, the computer does the mathematics and says, all right, I know for every hour in the next 7 days how much heating, cooling, and electricity I think my buildings are going to need. I know the equipment I have available to meet that, and I also know what the price of electricity is every hour of the next 7 days and my price of gas. I'm now going to put it in a mathematical grinder and lay out the mathematically optimum way to dispatch that plant. When to use heat pumps, when to take and put from hot and cold storage and all that. And it'll mathematically lay out the perfect optimal way to operate all that equipment to meet your loads at the lowest possible cost. And so that's why it's called model predictive control. You're modeling the future and using predictive control to plan it. Some simple examples are like I gave before. If you know it's hot today at your house and it's going to be cold tonight, and you probably need heat for heating or at least some hot water for showers and stuff. Model predictive control is simply just knowing that and saying, well, I know I need about this many BTUs tonight for all my kids' showers and laundry and stuff. So instead of throwing that many BTUs out in my air conditioning condenser today, I'm going to save that many BTUs in my tank to use tonight, and then we'll throw the rest away. That's a very basic example of model predictive control. So the question is, how can you prove how well it is? It's a great autopilot that does things. We actually had 5 two-person operating crews that are operating our system, and we had to train them to be able to operate the system manually in case the autopilot went down, just like a pilot would have to fly a plane if it went down. So we gave them the loads every hour of the year from the previous year, and we said, you tell us as the operators of this system how you dispatch the plant. Every hour of the year starting January 1st at midnight, show me which equipment you're going to turn on and off and at what setting, how many tons you're going to process, how much you're going to take and put from thermal storage. You guys lay out your best possible plan. And so we had the first of the 5 two-person operating crews do the first 10 days of the year, and then the next crew did the next 10. And we got to 50 days, then crew 1 started again. And that's so all of them had exposure to all the different days of the year. And when we got the full year's dispatch plan done that the operators said they would do, we then took that exact same load data and we put it in our computer and said, now tell us what you would do. So we have two side-by-side dispatches of an entire year's loads, and you can see the difference. On the left, the red line is electricity that's used by our buildings. And then we have to use electricity to do our heating and cooling with our heat pumps and stuff at our electric central energy facility. And when you add that electricity onto all the semi-non-dispatchable electricity the buildings use, you get the total energy electricity profile that you're going to buy off the grid, that the grid's going to see, in our case through our substation. And that's the orange line. So the red line is the building electricity use, and the central energy facility heating and cooling electricity use is added to that to produce the orange line, the total grid footprint. So the operator's dispatch is on the left and the computer dispatch is on the right. And the computer could do the same thing the human operators could do for 17% less peak and $500,000 a year less energy cost, plus a lot more reliability. So that was kind of the proof of this, the optimization model and the value of it. So we decided with all this to go build our new system, and the basic components you already saw: the heat pumps, thermal energy storage. We have a new high voltage substation, and once you go electric, you have to supply it with clean electricity. If you supply it with coal power electricity, you're not going to clean up anything. And so we built 70 megawatts of electrical storage just about 100 miles west of here, near Edwards Air Force Base, to power our campus. And of course the advanced software. We're looking at using some lakes on our campus and ground and other things to allow our heat pumps to suck heat out of these bodies of water in winter so we can completely stop burning natural gas. And all of this works really well at the house level, but for collections of buildings like the strip here, district energy would do it a lot better. There's a lot more diversity. If you can have all your equipment in one place supplying multiple buildings, you guys, a lot of you know, it's probably about 70% less equipment to use a central facility than having individual heaters and coolers at every place. People are concerned about reliability back east. A lot of people back east have told us, Joe, this is a Stanford thing. You got a mild climate, but it won't work in Boston or Chicago. We get ice storms, the grid goes down, blah, blah, blah. Well, in reality, the grid doesn't go down that much, even in those places. You see the news stories of it, right? And the ice storms and the ice hanging off wires and blah, blah, blah. It does go down once in a while, but on average, it's once a year for about an hour or two. And there are workarounds for that. The electrical heat pump system that we have and that you would deploy somewhere else actually can make heat 4 ways. It can use grid electricity to make heat with the heat pumps. You can take heat out of thermal energy storage. You can burn natural gas in our boilers, which have enough backup capacity to meet our total load, or you can burn liquid fuel. So I tell a lot of folks in New York that were, freaked out about Sandy and Hurricane Sandy and so forth, that no, going electric doesn't mean you have more risk of not being able to heat yourself in winter. You actually have 2 more ways, electricity and thermal storage, that you don't have with a cogen plant. So you have 4 ways to make heat with this system, which is more resilient. So there's the answer to the energy Rorschach test. So these are the actual heat recovery profiles of different facilities around the United States. Upper left is Stanford, big research campus. Our Redwood City administrative campus, now under construction, is to the right. It's only Monday through Friday day shift in session, as it were, the buildings are open. So we have a lot of cooling, but not very much heating because we're not there nights and weekends. And so the profile is much drastically different than main campus because of the schedule and type of facilities. Yet you can still see we can get over 50% of our heat just recovering our own waste heat from air conditioning, even at that type of facility. The lower left is the University of Illinois, Urbana-Champaign. It uses about 1.5 times as much energy as Stanford. And even in their ice-cold climate, they can get the majority of the heat they use if they just use their own waste heat from air conditioning. You see those big red parts, they have a lot more heating needs in winter than Stanford, obviously. Yeah, but they could use their heat pumps to just suck heat out of the ground and meet the bulk of that red too if they wanted. The same heat pumps that are doing all that work in winter could be used in summer, could be used in winter to with geothermal or ground source heat exchange wells, I should say, to just suck heat right out of the ground and make a lot of that. The very lower right is University of California, Davis in California's Central Valley. Weather profile is very similar to Urbana-Champaign, not quite as cold. But again, way over half of their annual heating could be made just by using the waste heat they've been throwing away. So the concept I explained before of total energy microgrid versus an electrical microgrid. On the left is the electrical microgrid that's in the news all the time. It's solar panels, plug-in vehicles, and batteries. Everybody should have that at their home, Tesla says, and Elon says he's probably right. Most homes in the future probably will have these components. But the thermal microgrid on the right is where 2/3 of the opportunity is with how you heat and cool, and it's where 2/3 of the economic savings are and 2/3 of the greenhouse gas savings and everything else. So again, you can see Stanford there, it's a total energy microgrid with the thermal microgrid having been developed first on the right with our heating and cooling system. And we've added photovoltaics both on and off campus. We're starting to see more electric vehicles. And we've been modeling a lot to see if electricity storage would be of value. We modeled it in 2012, and we've just modeled it again. And by itself, it doesn't pay for itself yet. Our thermal energy storage shifts so much electricity load, about 10 megawatts of electricity demand is shifted anytime we want, day to night, based on electricity prices by having thermal storage in this advanced software that says when we want to operate these heat pumps and when we don't. So if we didn't know about that and have that software, we might add 5 or 10 megawatts of batteries to our campus, and then later found out, crap, we shouldn't have. Thermal energy storage is far cheaper. A water tank will last 30 to 50 years and a battery 10, and it's 1/10 the cost to build a tank to store water than it is to build batteries. So we'll be deploying some batteries, but it'll be guided by that software where we add battery storage to the whole mix and have the mathematics tell us what might be of value, but it's not going to be very much right now. As our plug-in electric vehicle loads grow, we might be adding a little bit more to offset those demands to keep our peak down. But that's why for all buildings, thermal energy should be looked at and modeled first before jumping to the electric microgrid and throwing batteries at everything. So if you wanted to see if this would work for your house or your commercial building or your giant campus or your Las Vegas Strip or your downtown New York City, Manhattan, concepts are the same. Just get those 8760 tables of what the heating, cooling, and electricity demands are for the building stock you want to serve. And you can do the simple real-time overlap comparison I showed before of just taking the heat and cooling BTUs of every hour, taking the smaller of the two numbers, and you can develop these heat overlap charts that I've shown you. But then if you want to find out how you can get another 5, 10, 15% out of even that scheme, adding thermal storage and smart software, you could use a software like ours to model it all out, to optimize system design and show you just how much more you can get with all of that. We did all that, and we looked at all kinds of new systems. We're looking at an energy system for Stanford for the next 35 years. We looked at all possible new combined cycle gas turbines, internal combustion engine systems, hybrids of internal combustion engines, plus a small amount of heat recovery. And in the end, this is the chart we showed our board. Red is all the different bars of the different options. Red is how much capital Stanford would spend. Blue is how much operations and maintenance cost over 35 years we would spend. If we had to purchase natural gas, that's in the gold color. And if we purchased electricity, that's in the purple color. And we did our present value analysis over 35 years. We saw that sticking with our old cogen plan on the left, business as usual, and still sending steam to all of our buildings, far less efficient. It was going to be $1.6 billion or so. A lot of the natural gas options with very cheap gas were in the same ballpark as the electrification options. But the electric option was still a little bit cheaper, so we went with the clean electrification option you see there. And that was assuming we'd just buy our electricity from a local utility, PG&E, and have to pay whatever they told us. But we got the right then to buy our own power through direct access, it's called in California. So we could go out and build this solar plant and lock in these long-term 25 years of power at a nickel and stuff like this, and it's clean. And so we saved another $20 million over our original prospectus. Once we started building the plant, we got this, so it made it even better. So some other slides I didn't show you is that others are starting to realize this. So we looked at this in 2009 and concluded this was the best thing, and we had 5 different external peer reviews, all kinds of internal peer reviews, a full range of all options you see. We had like 10 major energy system options we were looking at, and had it peer reviewed out the yin-yang, and it was all confirmed it was the best way to go. It's been operating 3 years now and doing great and meeting or exceeding all its objectives. And it is possible to do it everywhere, even in cold climates, which a lot of people think it's not. But we've been kind of telling the story ourselves from like 2011 to 2014 and 15, but we finally got some help. The International Energy Agency's done studies that now show this. I don't show the references in here, but I could provide them easily. It's just the International Energy Agency Technology Roadmap for Building Heating and Cooling. United Nations came out with a big report in 2015. Our national labs, Lawrence Berkeley and Pacific Northwest, did the same study in 14, came up and said this is the way to go. And even Southern California Edison, who runs all the electricity in Southern California, just came out with a study in 2017, the end of last year, said, hey, we've looked at all the ways we can make power heating and cooling for buildings and reduce greenhouse gases in California. And the hydrogen highway isn't it, and the carbon highway isn't it, because you can't clean up carbon. The carbon capture and storage and biofuels, they're not economic or scalable. And so they said it's by far cheaper to go with clean electrification. And the way to get to clean electrification for building heating and power's obvious. You clean up the electricity making these lights, it's clean, right? Just put in renewables. Most air conditioning is electric, so if you clean up the grid, electricity, most of our cooling's probably clean. But how do you make heat without burning gas? Everybody's still stuck on that old mindset I showed you at the beginning of, well, we know old electric hot water heaters, terrible, don't do that. So we got these new efficient gas units in our garage. And we got these gas units, cogens at our universities and stuff. But the heat pump is the solution, and I showed you it's 1/3 less gas than a cogen plant or conventional ways of doing it. And so that's the key, is how do you provide heating to society without burning fuel, or fossil fuel? How do you do it with electricity efficiently? And it's all about the heat pump. And the heat pump first, using your own waste heat, that's always the cheapest and best, and then augment that by sucking heat out of the ground or air or a body of water. It's all still more efficient and cost effective than the way it's done now. And it's also the path to fully sustainable energy, but also stable and economic energy, because I know what my price to heat, cool, and power Stanford will be for the next 25 years. My capital's fixed. I've got a 25-year solar power deal at 5 cents kilowatt hour. I know exactly what it's going to cost, and it's cost a lot cheaper. I don't have to worry about gas prices and all that other stuff. So there's a lot of other good reasons for that. And with that takes us to time for any questions. Yes, sir.
Couple of questions. You showed a chart that showed manually running the system and then a computer model. So the difference where it was, okay, that chart right there. The difference between the left and the right is you don't see so many peaks, correct?
Yes, you can see the computer, the red lines are the same because that's the non-dispatchable background building. But here's what you get when the computer says, well, I know I got this. Now, how do I consume this much electricity to all my heating and cooling and come up with the optimum profile to present to the grid? It does those mathematics, and you see it's a lot flatter thing that has 7 megawatts less peak and also much less cost because lower demand and cheaper commodity.
The other thing is the storage tanks. You have to have the space. Not everybody, what's the size of those tanks?
So, I think 120-foot in diameter or something. But I don't know anybody that doesn't have the space. I've been at some very congested places, whether it's Harvard or different universities. In USC, they put them under a football field. I mean, there's all kinds of places to put a couple tanks like that. Every university I've been to has them because they know how important thermal storage is. All the universities are adding them thermal storage for cold. Nobody's doing hot because they're all using steam. And you realize, the super great benefits of cold thermal storage that everybody's adopting. If you move to supplying your heat with hot water instead of steam for all these other efficiency reasons, you go, wow, I can use hot thermal storage now and get all those same benefits. Lower capital, less equipment, shifting cost, having some heat and storage in case my plant. It's all those good reasons. There's almost always a place to put them. You can put them underground, you can hide them. Our plant's really beautiful. It's won the top AIA awards for San Francisco, State of California, and the ANIA Award for National Architecture. You know, we have a very particular campus in terms of our land is worth $5 million an acre, you know, in Palo Alto. And we have a pristine, beautiful campus with a certain architectural thing. They hit them so well inside our plant that you can't even see them until you go there. And when you do, you see how beautiful it is. And our plant is smaller in land area than our cogeneration plant was. So that's the thing we get too, is people say, I don't have room for these tanks. I bet you do, you know, if you just look. There's always a way. Yes, sir?
Love the idea of heat pumps. One of the things that sometimes you have to worry about for medium, low-grade heat recovery systems, because that's basically the type of temperatures you're often are in, is somebody will raise their hand and play the Legionella card. For these type of things where you're going all year round with what a more complex type of heat recovery system in a lot of these campuses, has that come up at all? Is that something that...
No, and one of the other beauties of heat recovery, you know, with a chiller, you send the water to an evaporative cooling tower, whether it's on the top of a skyscraper or on the ground, and that's where the Legionella, you know, issue can come from. With a heat recovery chiller, it's like the closed system in your car, like your radiator. You got cold water circulating in pipes around the campus. You send 42 degrees to the buildings. They get cool, and you get 56-degree return water back. And normally your chiller would suck that 14 degrees out and take condenser water that was received at 80, put that 14 degrees in, and send 94 out to the cooling tower to be cooled and come back at 80. So that's how the chiller works. With a heat recovery chiller, the condenser loop is your hot water loop. There's no cooling tower. So while I have 42-degree water going out to the campus and 56 coming back, my heat pump's sucking that 14 degrees out. I got another loop of water going through that comes back at 130 from the campus, gets heated to 160 with using that energy we took out of the cooling loop, and it's sent back. So you have these two closed water systems, heating and cooling loops, all connected by the heat pump. There's no evaporative cooling tower. There's no opportunity for Legionella or any of that kind of stuff in that kind of environment. It's closed loop. Yes, sir?
So you can kind of gain volumes and temperatures with the sizing your thermal storage. Out of curiosity, what did you all do for your thermal storage in terms of, are you storing at distribution temperature, or are you storing slightly elevated temperatures for heat and slightly depressed for cooling?
So the lower the hot water temperature you can get away with, and the higher the cold water temperature, closer to ambient, the more efficient the system will be. That's why you don't need ice storage and steam to heat and cool buildings, right? So we looked, and we have, you know, a 100-year-old campus with buildings of all different vintages and HVAC system design. We did a winter test to say, what's the lowest hydronic circulating temperature in the building we can get away with, even in cold days, that will still keep the building warm? And we determined it was 160. They had been operating some building hydronic systems at 180 and 190 because they had steam coming to the heat exchanger, and you don't need that much. So we set it at 160 so we could make sure we could satisfy all buildings. But again, with the new Redwood City campus, we said, look, we don't even really need 160. What if we just make our zone heat exchangers and main air handling unit heat exchangers work with 120? That should be enough approach temperature change to get 78 out of the register, and of course it is. So we're using 120 degrees circulating temperature there. That's barely higher than the condenser temperature of a regular chiller sends to a cooling tower. So you're almost getting free heat with you know, but 0.2 kilowatt hours extra put into the chiller. At the main campus, we have to put 1.5 kilowatts per ton into the big heat pump to get a high hot water. Redwood City, we only need 120, so it's 0.7 kilowatts. A lot of existing electric chillers are at 0.7. Brand new ones are at 0.5, right? So if you can go with the lower temperature, you know, you can save a lot of energy. And that's how we're able to do it with that winter test to prove our existing coils would work fine with it.
You just answered my question.
Okay. Right back there.
Do you use straight water or a glycol?
We use water in our hot and cold water loops. And the refrigerant's R134 in the particular heat pump chillers we have, but it's hot water. And the beauty part is, when we were looking at hot water systems, North America doesn't do it very much. There's only one place in North America we found that uses hot water, and that's District Energy St. Paul, Minnesota. And we talked to them, and they said, well, we learned from the Scandinavians in Europe. They've been using hot water to heat their buildings for a long time. And the Europeans developed this really beautiful system for hot water that's chemical-free. You raise the pH to 9.5, and you keep the dissolved oxygen super low, and you have no corrosion, and you have no chemicals. So if our hot water leaks, unlike our chilled water, there's nothing added. It can go right into streams and stuff. And the way the beauty of how you keep the water deoxygenized, instead of the regular deaeration things, deoxygenation systems you see that use chemicals and a lot of energy, you simply inject free hydrogen, H2. If you just inject free hydrogen into your hot water loop, it scavenges oxygen and makes more water. So it's this beautiful system the Europeans came up with that allows us to have a completely non-hazardous hot water. Our chilled water still has, a corrosion and biological inhibitors. So if it leaks, it's got to be treated as a hazardous waste. But our hot water, no, it's completely just water. It's beautiful. More questions? Yes, sir.
Information on the economics of it. Like the tough sell for me when I bring an idea like this to a customer is a traditional chill water plant's $1,000 a ton, right? Installed cost. And usually something like this is appreciably more.
Yes, so the first thing, I'm trying to find that present value thing. So the first thing is to look at it from a present value cost. So Stanford knows it's going to be around for many, many years. And so typical infrastructure is what, 30 years roughly? Pipes can be a lot longer. But if you're looking at making an investment of whether it's a couple million for a building or 300 or 400 million for a new university scale system, smart thing is to say, well, this stuff's going to last 30 years. I at least ought to look at the life cycle for that 30 years, not just like the next 5 years. Why buy a 30-year chiller or a 25-year chiller and only do a cost analysis of what it's going to take to run the next 5 or 10 years? So if you do that present value cost over 30 to 35 years like we did, you just see what comes out cheapest. You make independent assumptions about electricity and gas costs for the next 30 years, get your clients and others to say, hey, what do you think electricity is going to cost? What do you think is gas going to cost? All right, now let's look at these two systems. What do you use as a discount rate? What do you assume for inflation? You get all that stuff nailed so that you have an independent objective analysis for even start. You say, now let me lay out some systems. Given those parameters, you're going to come up and this is going to be cheaper in most places. And the big advantage clean electrification has that will come through when you do your calcs, it's using free energy. I mean, you've been throwing away, as you saw from these charts, all these places are throwing away 50% of the heating they do each year. They could be doing with just waste heat that's been going out cooling towers. For just slightly more electricity, you get all your heat through summer for free. No more really capital cost. As you can see on these things, the option we picked had a capital cost that wasn't as high as some of the others. Brand new cogen plants cost more because you're producing electricity on site. Bare bones systems, just boilers and chillers, you can have a little bit less capital, but they cost you a lot more in the long run. Water, we cut energy use at or water use at our plant 70%. Our cogen plant used 25% of Stanford's drinking water, but since 70% of the heat we used to throw away in evaporative cooling towers is now harvested and reused, the cooling towers operate 70% less. So we saved 70% of 25%. We saved 18% of our total water supply at Stanford just by doing this. And in arid regions like the West, that's huge. That would be great for Phoenix. So save water, save money, save greenhouse gas. Capital cost is not always the first thing. Now, it's unfortunate that developers have a short, payback horizon. And so society's got to find a way to get around companies that say, I may not be here in 10 years. I got to have the lowest upfront cost deal. I'll take a chance paying more. Or real estate developers that say, I'm going to develop a big building, but the renter's going to pay the energy, so I don't give a crap. I'll put in cheap systems. As soon as society starts connecting those dots, you won't see that anymore. And they're doing it with certain kinds of legislation and other things in different states where it's the building that has to be designed to be efficient. It doesn't matter who owns it and who's coming and going from the building. You got to divorce that motive from having an efficient building. You say, this is the cheapest building for society for the long term. And that's what building codes and incentives and other things are for, to spur this kind of thing. Yes, sir?
So I
design considerations when it comes to heat pumps. So, you know, when you're burning a fuel, you have a very high first hour recovery, and when you have you know, when you have a system that you have to supply the hot water, and you're going to have a recovery when people are coming in and everything is kicking on, did you have to, you know, gauge for storing a certain number of hours of
Sure.
intensity?
So-
What did you do with that?
Yeah, so we had two options. We do aggressive night setback at Stanford. So when people leave the building, if it's scheduled that the last occupant's there at 9 p.m., we'll turn those temperatures back down a lot, not crank them in until 6 a.m. for a 7 o'clock occupancy. And so with that, that's why our hydronic systems needed to be able to uptake heat faster. And so we had to make sure that, you know, the steam system could push that many BTUs in that fast for a quick startup. That's why we did the winter test, to make sure that we could flow enough 160-degree water. We can actually make our water up to 175 if we need to, actually up to 190 if we want, with our boilers, because our boilers can polish our hot water, make it even hot water that comes out of the heat pumps if we need to. We've never had to yet. But so we could deliver with the water system that same amount of BTUs for that quick startup. But you look at a university like Ball State in Indiana, they went to 4,000 ground source heat exchange wells and heat pumps to heat their campus. And they're only using 150-degree hot water supply. And we say, how in the dead of winter in Indiana can you get by with 150-degree water? They say, we just keep it circulating all the time. We don't do aggressive night shutdown like you guys do. You know, you can show that the total amount of BTUs you can flow out through your system over the course of 24 hours, even in cold weather. You can keep enough BTUs going to keep the building hot. You don't have to do it in a giant slug to start up. You can make it more continuous. That's how Ball State does it. We choose to aggressively set back and use thermal storage because it's cheaper in the long run, but you can still do it with a more constant flow of lower grade heat too. Yes, sir.
I guess just to clarify something you said a little earlier, if I understood you correctly, I think you were saying that there were heat pump chillers that are getting 0.5 to 0.7 kilowatts a ton. And the reason I'm asking is because we commissioned a heat pump, geothermal heat pump chiller system. We estimated about, I'm going to say about $250,000 a year of cost avoidance for a 1.5 million square foot facility. They were using screw machines and getting about one kilowatt a ton.
Is that their old or their new heat pumps that were being put in?
They were new. This was about 2 years ago. But I guess I'm just asking, what have you seen as far as chiller technologies or chiller manufacturers?
So some of it may go to scale. So when we looked for heat pumps at the scale we wanted, there's really only two companies in the world that made them at that scale, and that was York and a company called Ibarra, which doesn't do business in North America. Train and McQuay and Carrier were willing to do custom designed heat pumps for us, and we also got a bid from Vilter Refrigeration. But York, with their OM line and their YK lines, already have good off-the-shelf units. Now York's units, to get the temperature we wanted, 170 degree out, the performance curves for those units show that that takes about 1.5 kilowatts per ton, including the circulating pump. When we specified the lower temperature we needed for our Redwood City campus of 120, well, a lot more chillers can do that. So there's the selection of equipment was wide open for that. I can't remember if we picked Train or what model chiller we picked, but it's easy to find chillers that could put out 120. And the curves for that were 0.7 kW per ton at 120. And it jives because at 95, the curve is 0.5. So the higher temperature you need out, that electricity goes in. But the other beauty with a heat pump, with just a chiller, if you have 12,000 BTUs, 1 ton of cooling coming in, and the chiller needs to get rid of that waste heat through a cooling tower, well, that 0.5 or 0.7 kilowatt hours is converted to 4,000 or 5,000 more BTUs of machine heat, and you're exhausting 16,000 or 17,000 BTUs out your cooling tower. A heat pump, the 1.5 kilowatt hour turns into 5,000 to 6,000 BTUs of heat. That's added to the 12,000 BTUs from our cooling, and we get 17,000 BTUs of hot water out, productive use. So a heat pump is not only flipping your cooling waste heat to something productive, it's flipping the energy that goes into the chiller into an additional help or a good product, whereas with a chiller, it's an additional burden of load to exhaust. So that's the extra cool part about heat pumps is the electricity turns into productive heat. With a heat pump or chiller, it turns into additional heat waste, a burden that you have to get rid of. More questions? Yes, sir.
As we continue to go to net zero energy in California in 2020 and 2030, what kind of technologies do you see that you have to implement to get there, to get that 2030 NZE goals for Stanford?
So really, clean electrification is the solution for everything in society. I was at something called the Aspen Global Change Institute a year and a half ago in August, and I was there with these professors from all over the world. I was the only non-academic, and I was invited because of what we'd done at Stanford, but there's also a couple Stanford professors there and all over. And the whole premise of this week-long think tank exercise was how to decarbonize society and do it in an efficient way that's technologically adaptable, quickly. And the basic conclusion was that we have to electrify everything we possibly can and supply it with clean electricity. And again, the United Nations, IEA, Southern Cal Edison, everybody is now seeing that. Anybody who studies it will realize that. If you look at clean carbon or carbon capture and storage, carbon capture and reuse is only done in like 12 places in the world. You can Google it yourself, and 11 of them are in oil fields, and they're just injecting it to push more oil up. The Kemper plant in Mississippi was the first attempt to have a clean coal plant where they're capturing all the carbon and not emitting it. That plant's at over $7 billion for 600 megawatts capacity. It's 3 times as much as the 2 new Vogtle nuclear plants in Georgia, and so many more times than anything else. So carbon capture and storage has been proven it's just not going to work. And in terms of using clean biofuels, the scientists also show that it's non-starter. Specific little places like Dartmouth and New Hampshire that's got 30,000 acres of forest, yeah, they could set up a sustainable, grow the plant, turn it into fuel, throw a log in the fire deal. But for society as a whole, the total amount of energy the world uses, there's not enough land on the planet to do it. And then we wouldn't even have any land to grow food. So biofuels, clean fuel, won't work for the planet. It'll work for selected individual places. Carbon capture and storage, same thing. So the other thing the scientists come up with is hydrogen. Well, if we use clean electricity and split hydrogen off water, we can use fuel cells and all this other stuff that's clean, right? Because when you exhaust the hydrogen, you get water vapor. It's no big deal. But it takes twice as much renewable energy to fracture hydrogen off water to drive a fuel cell car as if you just put the electricity in the electric car. So Toyota and these other places proceeding with fuel cell cars, it ain't going to happen. They use twice as much clean energy as a Tesla or a Bolt or something. It just doesn't make sense. And there's no way to distribute hydrogen all around the country. We've got wires everywhere, so the electricity thing works. Well, anyway, this paper is going to be published in the Journal of Science very soon, and all these scientists say, we got to electrify everything we possibly can. There's no doubt about it. The real problem was the 20% of things now that are tough to electrify, and that's air travel, ship travel, long-haul trucking, cement manufacturing, and steel manufacturing. And with steel, it's very interesting. It's not because the electricity or energy used to do those processes you can't make clean. You could make all this molten stuff with electricity too. It's that with steel, the basic chemical process with ore releases carbon into the air from splitting the ore, the coke and all that. It's not the energy part. Same with cement. You're fracturing calcium carbonate to make the lime and things you need to make cement. So that CO2 coming out of cement plants, it's not related to energy use, it's related to splitting calcium carbonate up to make cement. So those are the 5 technological challenges the professors all said to clean up the world is ships, planes, long-haul trucking, cement and steel. And it was just a no-brainer. Buildings and cars and all this other stuff, it's got to be electrified and clean energy. It's the cheaper thing, and everybody's starting to realize it. And that's why I'm here to spur you all to start thinking of it for your buildings and facilities. Try and convince those owners that don't know about it why it's better, and it's the path to economically cheap energy too. I think we got 1 or 2 minutes. If there's 5 minutes. 5 minutes, the sign says. Any other questions? Yes, sir. Yeah, actually the economic Proforma that was approved by our Board of Trustees in December of 2011 assumed we'd buy power from Pacific Gas and Electric Company, and it was 10 cents a kilowatt hour delivered to our substation with an assumption of about 2% growth per year. It was only after that, and that economic Proforma is right here. This looks a little fuzzy here, but that's this one, and it was still the cheapest. Well, once we got direct access, our electricity cost went down about 20% and got cleaner. And we were able to go back to the board a year later and said, thanks for giving us $500 million to do this system. We thought it would save 300 and something million over 35 years. It's going to save 420 million actually because we got the right to buy our own electricity. So that was just icing on the cake. And I know it'll work in places like Illinois and others that we've helped look at this. They got 6 and 7 cent electricity power. And the cheaper the electricity, the cheaper the electric system's going to be, obviously. And they're also cleaning their power off coal. The other things people ask is, well, how clean does my grid power have to be to make this at least competitive sustainably with a gas-based system like cogen? If you move to an electrical grid that's primarily natural gas-based, the electrification option is cleaner than a cogen or other things because you save so much energy with heat recovery that a cogen in places and other systems don't. So if you can get off coal power and get to like 800 pounds a megawatt hour, which is a basic natural gas grid, the electrification will do better. But the good part about electrification is it's now the path. There's so many ways to make electricity. If you electrify, then you have so many ways to get that energy to be clean. Fusion reactors, wind, solar, hydro, nuclear, just so many different things you can do. And that also made it clear for our board. They said, look, we know these estimates aren't going to be precise over 35 years. Who can look that long at gas and electricity prices? But they're all in the same general cost range. So if there's not a clear economic winner that's 20 or 30% below one of the other systems, why wouldn't I choose the more flexible electrification option? It gives me so many more things I can do in the future than if I'm stuck with a natural gas cogen plant. I put that sucker in, I'm stuck for 30 years with it. So it was an easy decision to move to electrification because economics were looking a little better. You can't tell for sure for 30 years, but it's a far more flexible path. You can do a lot of things with electricity. It's got the best exergy, as the physics professors at Stanford tell me. It's the best fuel in the world for doing stuff. Most flexible. 1 or 2 minutes if there's one more question.
2 minutes.
Yes, sir.
How did you guys deal with pump redundancy and using that electricity to run pumps? Because I know now with the new ASHRAE standards and all the new LEED and other various organizations, they're all trying to cut down on pump runtime. And obviously, with this type of system, those pumps would need to be running all the time.
So we have pumps that push the water around campus, and we have pumps that drive the chillers and all that. The interesting part, if you come to our power plant, you realize it's just a collection of electric motors driving pumps and pushing fluids around. That's why our thing's so clean and quiet. But we have N+1 redundancy, number one, in all of our equipment. So we could lose our biggest piece of equipment at the plant and also meet our load. The second thing is that with thermal storage, you can greatly buffer. So a lot of people go to putting VFDs on equipment. They say, hey, I got this equipment, it's going to have to run like this all the time. Let's put VFDs on to smooth things out, right? When we looked at how our computer said we would dispatch our equipment, since a chiller has an optimum efficiency point on the curve, with a heat pump it's at the end of the curve. With a chiller it's just, it's like 90-95% of capacity. The computer is going to try and run all of that equipment at the optimum point on its curve to have the lowest cost. So when we looked at the 8760 table of what the computer said the equipment would be running, we found that 85% of the hours on our chillers and heat pumps are at its optimum operating point. There's almost no variable load because the thermal storage, you don't have to do that. You can baseload all your equipment at the precise point on its curve that's most optimum, and let thermal storage be your buffer on your take and put. You don't have to cycle your mechanical equipment to follow load. You can run it flat and let the thermal storage handle that. So no VFDs. It's a lot more efficient pumping arrangement, a lot less electricity draw, but we do have full redundancy on everything in case we lose stuff. You can't get away with pumps, of course, but you certainly don't have to cycle them like you do with regular systems if you have thermal storage buffering it. Yes, sir? Yeah. No, so it's just a big tank of water. So it's got some baffles where the pipes go in and out of the thermal storage to prevent turbulence. But so our 5 million gallon cold water storage tank, we've got 42-degree cold water in the bottom and the warmer 56 at the top, and there's a thermocline in between. And we have thermocouples, temperature sensors every 1 vertical foot of the tank, which is about 40, 50, 60 feet high. So you can graphically see the temperatures in the tank, and you can see all these 56s, and then you start seeing 54, 53, 52, and it quickly goes down to 42, and then 42. So you can see this 5 or 6 foot tall thermocline, but then the bulk of the tank is at warmer at the top and cooler at the bottom, so you can measure how much you, quote, have in storage. Same with the hot water, the 160s at the top, the 130s down below, and you have the thermocline in between, and you can always graphically see on your SCADA system how full your tank is. Computer software does that, measures it, and that tells you how much you have in thermal storage that it uses for planning how to run the plant for the next week. But it's just water. It's the same water that circulates out the campus in your chill water loop and the same hot water that circulates out in your hot water loop. They're interconnected. No special fluid or anything. She says we're out of time. Thanks so much.